We have two observatories, two LIGO observatories, one in Hanford, Washington, the other in Livingston, Louisiana. So these are very far apart, and that's the idea that if you are going to detect signals that are astrophysical signals coming from out there in the cosmos rather than here on Earth, then you would see them at about the same time in the two detectors with a slight time difference, not more than 10 milliseconds, because that's the speed of light between the two detectors. And this signal was the same waveform in both detectors, 7 milliseconds apart. Oh, it's going to be amazing. We have always said that this is going to be a field called gravitational wave astronomy, because we were not after the first detection. We are, of course, so happy about this first detection, but it's only the first. What really matters is that all the ones that will follow. We are going to be detecting signals from black holes and neutron stars, and these are all colliding and forming new black holes. And we can compare the waveforms that we measured with those waveforms that you can calculate with a theory to see if there is some variation to the theory. We can call this a test of general relativity, but I think more important than that, we will be measuring how big black holes are, where they are, how many there are. With neutron stars, we'll be able to tell what's happening inside the neutron stars. We don't know as much as we think. It's not such a clean system. And we will be able to tell from looking at that last part of the neutron star merging with another neutron star and forming a black hole. We'll be able to tell what was inside that neutron star, what's what we call the equation of state. And this is astronomy. This is about identifying stars, identifying properties of stars. But now we are talking about stars that you cannot easily see with electromagnetic light, with electromagnetic waves. And if you see them with electromagnetic waves, then it's even better, because you have two ways of looking at the same system. You have the electromagnetic wave, which will be either light or gamma ray bursts or X-rays or radio waves, whatever is coming from that system. And you have the gravitational wave, which is a completely different signature, because the gravitational wave is telling you about how the mass is interacting with space-time. The electromagnetic waves are telling you how the photons and the atoms in there are interacting. It's monumental. It's like Galileo using the telescope for the first time. It's, of course, it's different because we have been waiting for this. We have been working for this for decades, so we knew it was coming, but that makes it even more exciting because we've been waiting for this for so long. But it's just a first monumental step in gravitational wave astronomy. It's the beginning of a new field. The fact that we don't compete with each other, even with our collaborators. We have the LIGO collaboration that also has a detector in Europe, the geodetector, but we have taken data in the past with a detector in Europe, which is part of a European collaboration, the Virgo collaboration, and we analyze the data together, all together, the Virgo collaboration and the LIGO collaboration. We all look at each other's data and analyze it all together. They don't have their detector ready yet. We are going to incorporate that detector next year. But then again, it's the spirit of we don't have two collaborations saying who detects it first, who detects it better, and then we compare results. We work together. and that, I think, it's something I like about our field.